In this section, we're going to take what we've learned so far about plotting polar points to create some graphs of polar equations. So let's take a look at some of these polar equations. Like rectangular equations, polar equations involve an input and an output. In a rectangular equation, the input and the output are typically x and y, where when written as a function, we might say y equals f of x. For a polar equation, the input and the output are r and theta, where when written as a function, we would say r equals f of theta. Now, why use polar equations? Polar equations involve very simple equations, as you'll see here in a minute, that produce some really amazing results. And those results oftentimes look like everyday things around you. For example, the polar equation of r equals a times the sine or cosine of the quantity n times theta is called a rose curve. And it's called a rose curve because it sort of looks like a rose, or in this case, a flower. If the n value is odd, then there are n petals. If the n value is even, then there are 2 n petals. And of course, a cannot equal 0. We'll look at some examples of this in a minute. Another example of a polar equation is something called a lemniscate. And a lemniscate looks, you can see in this image, looks like a sound wave that almost looks like the infinity symbol. Now, graphing that with a polar equation, the equation is r squared equals a squared times either the sine or the cosine of the quantity 2 times theta, again where a cannot equal 0. And finally, we have the graph of the polar equation that's called a limacon. And a limacon, the equation for that is r equals a plus or minus b times the sine or cosine of theta, where a does not equal 0. Now, the different types of limacon, there's one called an inner loop, and you can see that inner loop on the inside. There's one called a cardioid that looks like a heart. That's why it's called the cardioid. You know, think of cardiology as a heart doctor. Or there's one called a dimpled limacon. And you can see in this picture of the apple that it sort of looks like maybe a cardioid that's reflected from this picture. Now let's look at an example where we are asked to graph a polar equation. Identify the shape of the polar equation, r equals 3 times the sine of the quantity 2 theta, and then graph the polar equation. So, using the equations that we've learned about rose curves, lemniscates, and limacons, which one of these seems to match the form that we're given of r equals 3 times the sine of 2 theta? I think that this looks like a rose curve because we have an a value being multiplied by the sine of the quantity n times theta, and that appears to be what we have here with 3 times the sine of 2 theta. Now, it appears that our n value is 2, and because 2 is an even number, I'm going to expect 2 times n petals. So 2 times n petals, which will give me 4 petals, right? So I believe that this is a rose curve, but we will see here in just a minute. All right, so let's now produce, let's look at a graph. Let's see how we might graph this. So what we want to do to graph it is we want to just come up with a table of values, and then as we come up with that table of values, we will plot those points. All right, so I've created a little polar graph here for us. Hopefully that helps. So we're going to start, let's just start with 0, and we're in radians. So if I input 0 radians into this equation for r is going to equal whatever 3 times the sine of 2 times 0 is. And let's see, 2 times 0 is 0, and the sine of 0 is 0, so this becomes 3 times 0, which is 0. So our very first ordered pair is the ordered pair 0, 0, right at the origin or the pole. All right, now my next theta, I could pick anything I want. The closer the values are for theta, the more precision I'm going to get with my graph. So I'm going to choose pi over 6. If I were to pick, say, pi over 4 or pi over 3, they're spread out more, and I may not be able to see the shape quite as well. All right, so this is going to be 3 times the sine of 2 times pi over 6. Now, that's the same thing as 3 times the sine of 2 pi over 6, which is pi over 3. And you might want to pause the video here and figure out what is the sine of pi over 3. But assuming that you have some of these things easily memorized, that's going to be 3 times the square root of 3 over 2. And because I want to plot this, I'm going to go ahead and put that into my calculator. And when I put 3 times the square root of 3 over 2 into my calculator, I got approximately 2.6. So I'm going to have a radius of 2.6, and I'm going to have a theta of pi over 6. So let's graph that, and I'll pick a different color maybe. So let me put my point at the origin or the pole in blue. And then I'm going to go to pi over 6, and I'm going to go out to a radius of, let's see, 1 and 2, and there's 3, so 2.6 is maybe right there. Okay, let's do another point. So 1 pi over 6, let's try 2 pi over 6. 2 pi over 6 is going to be pi over 3. So I'm going to have 3 times the sine of 2 times pi over 3. And go ahead and pause the video on that and figure out what that should be. I came up with 3. Let's see, the sine of 2 pi over 3. The sine of 2 pi over 3 is also square root of 3 over 2. So same output of about 2.6. Now you might think, oh, it's going to be the same point, but remember, we are now at a theta of pi over 3. So going to pi over 3 right here. I was at pi over 6, now I'm at pi over 3. I'm going to also go out 1 and 2 and just a little bit past that, so maybe right there. And then let's keep going. I think we should be seeing a pattern here. 3 pi over 6, that's going to be pi over 2. So 3 times the sine of 2 times pi over 2, which is going to be, let's see, 2 times pi over 2 is just pi, and the sine of pi is 0. So 3 times 0 is 0. So I think what has happened is we are back to the pole. So let me just graph, maybe connect some points here. We started at the pole. We went to this point, 2.6, comma pi over 6, and then we came back around and we ended up back at the pole. That is our first petal. And because we said that we thought this would have 4 petals, I think you might be able to see the pattern that is probably going to happen. I'm guessing that there's going to be a petal in each quadrant, but let's just do a few more of these. All right, so we did 3 pi over 6 last. Let's do 4 pi over 6. 4 pi over 6 is 2 pi over 3, isn't it? So 3 times the sine of 2 times 2 pi over 3 is equal to 3 times the sine of 4 pi over 3. And let's see, 4 pi over 3 is in the third quadrant, and so that's going to be a negative square root of 3 over 2. So I have negative 2.6. So negative 2.6, comma, 2 pi over 3. Let's just see what that looks like. So 2 pi over 3 is in the second quadrant, but with that negative radius, I have to travel across it to 5 pi over 3. So let's see, there's going to be 1 and 2, and I'm going to be about right there. Okay. All right, let's keep going. So 5 pi over 6, so 3 times the sine of 2 times 5 pi over 6. 2 times 5 pi over 6 is 5 pi over 3. And the sine of 5 pi over 3 is also negative square root of 3 over 2. So I'm going to have negative 2.6 comma 5 pi over 6. So again, we are 5 pi over 6 is in the second quadrant, but with that negative radius, we have to go across to 11 pi over 6, and that's going to put me about right there. And I feel as though I know what's going to happen with the next point, but let's just see here. 6 pi over 6 is equal to pi, so 3 times the sine of 2 times pi. The sine of 2 pi is 0. So we are back at, let's see here, 0 comma pi. So if I'm at a radius of pi, if I'm at a theta of pi and a radius of 0, I'm just back at the pole, aren't I? So let's plot this out. So from that first quadrant petal, we now created a petal in the, looks like the fourth quadrant. Okay, so I'm guessing if we keep going, do you think I'm going to end up in the next one's going to be in the first quadrant, or is it, or excuse me, the second quadrant or the third quadrant? Well, let's maybe just do one more to see where this thing's going to go. So 3 times the sine of 2 times 7 pi over 6 is 3 times the sine of, let's see, 2 times 7 pi over 6 would be 7 pi over 3. And 7 pi over 3 is one whole rotation around, and then ends me up coterminal with pi over 3. So this should be square root of 3 over 2. So 2.6 comma 7 pi over 6. All right, so 7 pi over 6, where's that? That is in the third quadrant, and I'm going to be at a radius of 1 and 2 and 2.6. So it's a positive radius, so I'm staying in that third quadrant. All right, I'm going to let you fill out the rest of this chart. Now that I know that that point is in the third quadrant, I feel as though I can probably guess that that third petal is in the third quadrant, and the fourth petal would be in the second quadrant. So now let's take a look at how we might graph that same polar equation, but using technology. We're lucky that we have technology because graphing by hand was a lot of work, wasn't it? So I want to show you how you might do that with Desmos, and then also show you how you might do that with a handheld graphing calculator. So let's start with Desmos. And so you're going to go to the normal place in Desmos, but you're going to go up to the wrench and you're going to click that to a grid that's a polar grid. And of course, make sure that you're in radians. Once you've changed it to the polar graph, you now have the ability to graph r equals and also have things like theta. Now you can type the word theta, or you can go to the keyboard and find the theta. And look how fast that was. All that work we did before is now so simple. And if I change the theta, I can see, like if I go from 0 to pi over 6, I see that first movement. I can step by step see how we created that first petal, and then the second petal, and the third and the fourth petal. All right, so that's pretty nice, isn't it? Now, if I go to the graphing calculator, a little bit more work. You're going to go to mode and you're going to change it. Make sure you're in radian, and then go down to where it says function and you're going to change to polar. All right, now once you change it to polar, now when you go to y equals, it's actually r equals. So you're going to type in 3 times the sine of 2, and the theta is in the same position as where the x was before. And when we graph it, there is the picture. I'm going to go to zoom square. That's going to set that rectangular window into a square window. And maybe I'm going to zoom in a little bit so that I can see it closer. So that looks pretty nice. If I use the trace feature, I can actually see the path of that petal being formed. So we see the first petal, the second petal in the fourth quadrant, the third petal, where did that end up? The third petal ended up in the third quadrant, and making my way all the way around to finish out that rose curve. The other thing that I can do is I can take a look at a table of values. And so I go to table set, and I'm going to change that triangle means the change in the table. I'm going to change that to pi over 6 because that's what we did. Pi over 6 is approximately 0.52. And now if I use the table, I can jump from, remember I said it was like 2.6, and you can see that 2.6 for the radius, and you can track that all the way down to 2 pi, and then after that it would just repeat itself. So that is how you would graph with technology. We also know how to graph by hand, but really all that I'm wanting you to do is be responsible for graphing using technology. So make sure that you can do that.